him like 3 minutes after.
Recording in progress.
Okay. And then let's wait. I mean, now it's exactly 6 o'clock. I mean, let's wait. I mean, at least on my time zone. I can wait a few more minutes.
Ronnie, you're the moderator of this session? I mean...
No.
Who's in control?
It's me.
Giuseppe.
Oh, no. I'm sorry. Who's in control of the Zoom?
It's Oleg Isaev from the conference organization. So this is the icon with LPHYS'23 Seminar 2. But it's easy. So every participant has the right to share the screen. So
okay. So it's not being done as a webinar.
Yeah.
Hey, Barry, are you there?
I'm here. I'm waiting. Why? How's it going, boss?
Okay.
Good.
Virtual lab background. How fancy is that?
Looking forward to your talk, Lou. Looking forward. It's good to see you.
Good seeing you.
This is more looking like a real lab background, right? Not virtual.
So, Lou, should we start?
It
will be fine for you? Okay. So, good afternoon, everyone. So, it's a pleasure to chair this afternoon session of Seminar 2. And for those of you, I mean, I know a few names, I know also a few faces, but not all of you. I am Giuseppe Sansone from the University of Freiburg. So we will have 2 invited talks in this session. The first one will be given by Luigi Mauro from Ohio State University, and he will talk about building a quantum trajectory selector for studying strong field physics. I will mute myself and also kindly ask you to keep your microphone muted during the talk. Please, Lou.
Thank you, Giuseppe. So you see in a flower?
Yes.
Okay. Okay, now you see my...
I see your presentation. Yes, now it's...
okay, let me just...
Now it's fine. No, okay.
Okay, and you see the laser pointer?
I can see the laser pointer.
Okay.
I see a double big picture of the presentation, but maybe... Could be fine. I mean.
Okay. All right. Well, thank you, Giuseppe. And I want to thank Ronnie and Christoph for inviting me here today. And I'd like to tell you a little bit of some very recent work we've been doing. It's something I am excited about. Let me just get rid of this. Okay. So I want to talk about what we call a quantum trajectory selector and how to build one. Okay, so let me start off by just reminding everyone, and everyone here is very learned, that the three-step model, which is now is 30 years old, the three-step model was a kind of intro into the attosecond world, right? This three-step model, which was very intuitive roadmap for thinking about strong field physics, also very intuitively said why the physics is subcycle, okay? And because of that, the three-step model provided this roadmap that within 8 years we had discovered the formation of attosecond pulses, okay? And as you know, that was done both simultaneously in Vienna and in Paris, okay? So I would say that strong field physics enabled attosecond science. And what I like to do today is kind of, reverse roles. In other words, how can we now use attoseconds to learn more about strong field physics? Okay, and I hope to convince you that this is a new paradigm for performing and broadening strong field physics, and I'll try to demonstrate that to you in this talk. So I think everyone here is familiar with the three-step model, tunneling followed by propagation in the field, and then those trajectories that return could recollide with the core. So this very intuitive picture of strong field physics is defined by tunnel ionization. That is, its initial conditions are defined by tunneling. Afterwards, the field dominates in step 2 and drives step 3. Okay. Okay, so here's a different view of it. We have some infrared field. Electrons are tunnel ionized, forming a wave packet. That wave packet depends upon the tunneling rate, and that tunneling rate is exponential in the field. So the initial conditions are defined by the extrema of the field. And of course, this happens from half cycle to half cycle in a single frequency field. And certain trajectories, as indicated here in purple, could return to the core and interact with the core. Some trajectories like this one just drift away and don't interact with the core. But we know that this simple picture helps explain things like how you get high energy electrons in the photoelectron spectrum. Here you see a series of photoelectron spectrum taken at different intensities at 1.7 micron excitation, and you see the clear classical signatures in it. You see kind of like the 2UP break in the photoelectron distribution, and then that extends out to the classical limit of 10UP. Likewise, if the electron recombines back to its ground state, then you get high harmonic spectrum, and then the high harmonic spectrum is characterized by this cutoff, which again is a classical signature of 3.17 UP. Likewise, if the electron returns, the field-driven electron returns to the core and has sufficient energy, it can knock off a second electron. And here you see the experiment that was actually done by Barry Walker, who's online, where he studied very carefully the non-sequential double ionization in helium. And of course, the mechanism here is due to essentially E2E scattering, inelastic scattering. So let's examine the characteristics of the tunneled wave packet, since this does define the initial conditions in the strong field. Well, kind of all tunneling wave packets look the same. They get filtered going through the tunneling barrier. They're born outside the potential well, that is on the outer turning point of the Stark potential, and they're born with near zero velocity. The wave packet, again, is peaked at the extreme of the field, so the initial phases are limited by that exponential rate, and then ionization is highly nonlinear, that is tunneling, and that limits the range of intensities that one could measure in a real experiment. So the experimenter has some control, but limited control on these initial conditions. And the concept that I'll now introduce of the quantum trajectory selector breaks out of this constraint. So this is so let me do that. So here's the basic idea. We're going to replace tunnel ionization by single photon ionization by an attosecond pulse train. And look at the cartoon here on the right. It's showing you that we can control the relative phase between the attosecond pulse train and the infrared field. The condition, though, that were the key conditions we're looking to mimic tunneling is that the single photon ionization produces a near zero energy electron. So we want to excite or shape our XUV at the threshold of the atom or molecule that we're studying. The duration of the attosecond pulse should be sub-cycle. So we have the ability now to select trajectories at any phase we choose. And the only kind of technical requirement is that the attosecond pulse train is phase locked with respect to the infrared field, and that is done in the common way since the infrared field is making the attosecond pulses. So this is a rather old idea, and some of you are probably familiar with some of the attempts in the past. And what I'd like to do is go through some of these seminal papers. So dating back to 2005, there was a theory paper by Meta Gar, Ken Schaefer, and Ursula Keller that introduced this idea of trying to use seeding with an attosecond pulse train to enhance high harmonic generation. That was followed in the subsequent year by an experimental demonstration where they saw enhancements of the harmonic spectrum that in helium seeded by harmonics from a xenon source, a xenon jet source. What they saw are rather modest enhancements on the order of 3 to 4 in amplitude. And at that time, all they extracted was the amplitude information in this experiment. This was followed by an experiment by Mark Vrakin's group. Mark also saw similar enhancements to that of the earlier studies, but Mark was also able to demonstrate the dependence of the on the dependence of the delay of these harmonics. So the little cartoon there plots 3 different harmonics as a function of delay between the IR and the attosecond pulse, and you see it oscillates, and it's oscillating at 2 omega. A latest study was done by Nurit Dodovich, and what Nurit did is extend this earlier work of Vrakin to include an interferometric measurement. Again, they saw a similar enhancement. I would say they did not learn that much about the recollision process itself as much as learning about the initial conditions for this seeded enhancement. Now, these were all very interesting experiments in their own right, and gave us a preview into what attosecond control might look like in an experiment. But there were two competing conditions that impose limitation on these experiments. First of all, if you're going to build a seated setup, what you would like to do is to have the ionization rate from the attosecond pulse train to dominate over tunnel ionization. But in the same condition, you would also like a large enough pond motive energy in order to drive recollision. So all these experiments were done at 800 nanometers. And this is a challenge for these experiments at 800 nanometers. And I hope to explain to you why that is. And what we're doing that is fundamentally very different. To essentially make a fully functional quantum trajectory selector. So again, the idea of the selector is to study recollision induced strong field processes. We replace the strong field tunneling step with attosecond XUV ionization from an attosecond pulse train. And then we use an intense phase lock mid-infrared field to drive the propagation. So the prerequisite to have a functional QTS, quantum trajectory selector, is first of all, if I'm going to mimic tunneling, what I would like to do is scope my XUV light such that it's at threshold. That is to say, it creates a near zero energy wave packet. Okay, I want UP to be large, so I can drive recollision over large dynamic range, and the rate of single photon ionization from my XUV attosecond pulse train should exceed that of the rate from pure tunnel ionization. Ideally, I would like to shut off tunnel ionization completely. And our solution then is not to do this at 800 nanometers, but to make use of the lambda squared scaling at longer wavelength, okay? So this will allow us to have large pond motive potentials, but keep the tunneling rate to a minimum such that our attosecond pulse train dominates the ionization. So I sent this poor guy here, Dietrich Kieswetter, a former student of mine, into the lab. This was something we've been thinking about a very long time, trying to figure out how to, overcome these limitations of some of the early experiments. And Dietrich went in and, took some of our existing apparatus and tried to do proof of principle. And indeed, he was very successful at that. And that kind of motivated us then to make a dedicated device for studying this quantum trajectory selector. So here's schematically what the apparatus looks like. Let me just tell you the few of the features that made this a very successful experiment. So our fundamental fields are anywhere between 1.8 and 2.4 microns, okay? We tried to generate as bright as an XUV source as we can. In the past, we were using xenon. This has become prohibitively expensive, and we have discovered other ways of actually getting very bright XUV pulses, which I won't talk about. We use both omega and omega 2 omega schemes for generating attosecond pulse trains. Then we use multi-layered mirrors and filters, metal filters, to shape the APT. So here you see an example on the right, and what you see here is this is a shaped attosecond pulse train for studying helium. It essentially has its maximum around 26 eV, so very close to threshold in helium. And then both the mid-infrared and the XUV are recombined and then delivered to a coincidence apparatus that has both electron and ion detection. So we started these experiments back in 2021, and I'm going to tell you a bit about them. But let me just acknowledge that this apparatus was built by three very competent people: Andrew Piper, a former student; Joey Liu. Joey is actually graduating in September; and then my postdoc Yaogao Tang, who actually continues these experiments. So the rest of the time, I'm going to talk to you basically about the quantum trajectory selector applied to argon atoms. So for argon atoms, then we want a different shape pulse. Note now I'm showing you a logarithmic scale, and you can see the harmonic spectrum, and you can see the harmonic spectrum is peaked near zero energy. We can tune the position of that strong harmonics at near threshold by just changing the fundamental frequency a bit. Okay. In this case, we use indium filters in combination with a multi-layer mirror, which is has its reflectivity maximized at 6 eV. Okay, we thought a clear signature of whether we're driving recollision is to look for double ionization in argon. So first we put in our infrared field, we see that we have very little double ionization from argon from the mid-IR alone, which in this case is 1.7. So what you're seeing in the upper panel is a spectrogram from the mass spec. So this is the mass of the argon 2 plus. And the thing I want you to notice is that the yield of the argon 2 plus is oscillating. It's oscillating at 2 omega, as you would expect for the attosecond pulse train in this case. 3 UP for the combined IR UV field is approximately that of the binding energy of the argon plus. That is, there's about 30 volts of return energy on this wave packet. And as I said, the mid-IR alone does not generate much ionization, and plus it's not phase dependent, obviously. And here's a line out of that spectrogram, and you can clearly see this oscillation over many cycles. Okay, so this result suggested to us that the QTS pulse approach is driving the E2E in argon atoms through the recollision process. So let's take this now one step further. What I'd like to do is try and time the double ionization against the photoionization, that is the electrons themselves. So now you're looking at two spectrograms. The upper spectrogram is just like the one we were looking at. It's the argon 2 plus as a function of delay between the IR and the attosecond pulse train. You see it's oscillating at 2 omega. Down below is the photoelectron spectrum that is taken simultaneously, and you can see the photoelectron energy is streaked by this attosecond pulse train. This is not a rabbit experiment, right? It's a strong field, so it's in the non-perturbative regime, and so it's very similar to the streaking done with isolated attosecond pulses. So what do we know about this spectrum? What we know is that the maximum in the streaking occurs at the zero of the electric field, or to say it the other way, it occurs at the maximum of the vector potential. So that defines T equals 0 for us. So the blue line here indicates where T equals 0 is at the maximum of the vector potential. And then what we do is analyze the phase between the photoelectrons and the double ions. And what we see is that the maximum in the argon 2 plus occurs 0.3 mid-infrared cycles after the electric field node. Okay, this result is completely consistent with the fact of semi-classical expectations. That is, we're seeing that the argon double plus is maximized at the point where the return energy is maximum. We actually have a model, which I'm not going to present to you, that very much models these results. Okay, what happens as we lower in the intensity? So in this case, the mid-infrared field has enough return energy to directly ionize the argon plus and lead to an E2E process. As we drop the intensity, so again, you're looking at spectrograms. I guess this is just the electron energy in the double ion. As we drop the intensity below the condition where 3UP is equal to or less than that of the argon plus binding energy, we continue to see the production of argon 2 plus. So the phase difference that we observed in this experiment remains at around 0.3 mid-IR cycles. And what this suggests, in fact, that we can model is what's happening here is we have collisional excitation of the argon ion followed by ionization by the mid-infrared field. So here's an example of where we can study the strong field physics in a regime that you would not access in, say, a traditional single, a strong field experiment. So let's take this even further. Let's now clock the rescattered electrons, that is, the electrons that underwent elastic scattering against both the double ion and the direct electrons. And here's the result. I'll ask you to just focus again on the panel of the lineouts on the right. And what you can see is, again, we see this 2 omega oscillation. We again use the direct electrons to define our 2UP point, or our time equals 0 in the electric field, that is at the node. And now we can clock both the double ion and the elastic electrons against this reference point. And what we find is that the argon double plus, just like we saw earlier, is about 0.3 mid-IR cycles, but the recollision electrons consistently occur at a phase that is slightly earlier than that of the double ionization. And again, this is consistent with the idea of the semi-classical model that one would expect in terms of where the maximum point in the elastic process, that is where the 10UP electrons always are the result of actually long trajectories that is slightly earlier than the maximum return energy. So let's me end by talk about future studies, and I hope I've convinced you that this quantum trajectory selector really is a new paradigm for strong field physics. And let me point out things you can think about doing now. Okay, now you have robust control of the initial conditions and the propagation conditions. Complete control. I don't have to make a zero energy electron. I can put kinetic energy into my wave packet and study the strong field process either with kinetic energy that are positive or negative. I can also stop thinking about just excitation from the valence state and think about doing excitation from core states and then driving that wave packet again, in the strong mid-infrared field. Of course, our interest is, our initial interest was to see if recollision worked, and that's what I presented to you today. But we're really more focused on looking at non-classical behavior in strong field, where many experiments through the years have indicated kind of the breakdown of the semi-classical model. And then the other thing is I can think about interrogating molecular dynamics and structure. And let me just show you a teaser here. Here is the ionization of CO2, okay, with an attosecond pulse train in a mid-infrared field. And what I'm showing you here are lineouts of spectrograms. And what you can see is we see the double ionization of carbon dioxide oscillate at 2 omega, but we also see the fragments that are oscillating, the CO, the carbon, and the oxygen ions are all oscillating at 2 omega. Right now, I can't tell you what the phase difference is between these, but we expect that we would learn a lot by analyzing the phase. And finally, I guess the big question here I want to raise, and something we're continuing to think about very carefully, is this quantum trajectory selector actually a simulator, whether it be a classical or quantum simulator of strong field processes, and something we can exploit into the future. So with that, I'm going to end. Let me just acknowledge people here. I've introduced the 3 people who are working on the experiment. Also, the theory part was done by a collaboration between Ohio State with Abraham Camacho and at LSU with Ken Schaefer and Jens Backhoff. And with that, I thank you for your attention, and we'll be glad to take any questions.
So thank you very much, Lou, for this very interesting talk and these nice results. And of course, we have time for questions. So we are not so many. You can simply unmute yourself and pose the question. Barry.
So Lou, very nice. And I have a question, because in addition to creating near zero kinetic energy photoelectrons in the continuum, the attosecond pulse goes down into the Rydberg states. Is that correct? And so then if these are excited, they would ionize trivially in any sort of strong field. So I know you've thought about this, but that's like that's my little conundrum.
That's an excellent question, Barry. In that case, there wouldn't be a phase dependence, right? The phase dependence comes about because of the recollision. So indeed, there could be trivial, what you're describing is a sequential process. That itself, if it was, neutral bound states, that won't lead to E to E. You would have to actually excite some type of autoionizing states. Okay, we have evidence that some of this is going on. It's rather interesting. We don't completely understand it. And that's, again, more food for thought in the future.
Okay, great. So then, in other words, these Rydberg states are possibly there, right?
Yes.
And then, but they are not ionized by the infrared pulse directly by tunneling.
No, they are ionized. So
okay.
If we scan over a longer range of delays, such that now the IR and XUV are completely separated, if the XUV comes first and the IR second, at long delays, you'll see that there's an asymmetry. So there is XUV excitation followed by ionization. Okay, that's something we can control because we can shape a bit the XUV spectral content. by playing around with filters, and we have different multi-layered mirrors. But indeed, that some of that is going on. The more interesting thing is, so that goes on basically for the lifetime of the Rydberg state. So we can, scan very long picoseconds and still see it. But there's also a component of population that's a DC level, but it's transient. So it exists for some time afterwards, after the two pulses are well separated, which would indicate that we're possibly exciting higher line autoionizing states and seeing their decay.
Okay, I didn't know if you were recreating a Zeke experiment. You know what I'm saying?
Yeah.
Thank you.
Any other questions?
Yeah, I think I'm having the same question effectively, but if the attosecond pulse train would below threshold, I mean, it would create a wave packet in these Rydbergs, right? Mm-hmm. So would that, some of this, some eigenfrequencies of this wave packet would also translate into the long time evolution of your measurement, right? So for the large delays, effectively.
Yes, that's right. It depends, of course, where the comb is lying and how much. I mean, those wave packets are going to oscillate at the characteristic time of Rydberg states, which are very long-lived states, right?
It depends on how many you coherently couple, right?
How many coherently you create. That's correct. So there's no doubt that some of that is going on, Martin. But this is not the dominating effect that I showed you today.
No, sure. That's clear. I would like, if you wait 200 femtoseconds and then you sample again, and then I would expect maybe you see some residual modulation.
Yeah, I think, both of you guys have pointed out, the richness of this experiment, the various phenomena that we can now access that we couldn't access before.
Yeah.
So everything is good at this point.
Maybe a question from my side, Lou. Because we are creating with the attosecond pulse train these electrons with a very low kinetic energy, almost at rest. So you might have that some part of the photoelectron wave packet will reveal several times the parent ion because of the IR field. Do you see any effect in your photoelectron spectra, kind of phase shift induced by the ions, or do you think it will be possible to see this?
I think it will be possible to see the effect. Yeah, so basically, can I distinguish between contributions from the long and short trajectory? And I think the spectrogram I'm showing you has those elements obviously in it. Because we are selecting subset of trajectories, right, at any particular phase we work on. So I think the answer is yes. We should be, we're still trying to understand the precision at which we can extract these or clock these processes. Right now, it seems to indicate that we're being able to clock them with about 150 to 200 attoseconds. But as we refine that, which is going to require, of course, stability in our system, we may be able to look at these kind of finer delays
that you need in me. Okay. Okay, thanks. So I'm looking around if there are other questions. So, but I don't see any. So, Lou, thanks again for your talk. Thanks a lot.
Let me stop sharing.
Okay, and then we can move to the second talk. This will be given by Martin Schulz in University of Graz. He will talk about ultra-fast light to steer electronics and switch magnetic moments.
Thanks, Giuseppe, yeah, and thanks, Reini and Christoph, for the opportunity. Now, the cool thing is I'll be giving Lou's talk. Just we have to figure out how many slides you need to notice it's the same. So let's see. The first thing, of course, I noticed is that there was a typo in the title, so I didn't like it. I changed the title slightly. So I want to show you very brief three experiments we did where we attempt to use ultra-fast light pulses to remote control electrons, electronic structure, if you want, currents, and remote control magnetic moments. Now, to shine a laser on something and change it is easy, right? You can always burn a hole. But that is, of course, in the terms of how I would want to use control, it's not really control because it's not reversible, right? Control would be if you can, if the system can be deliberately made to change its state, and then also if ideally you could bring it actively back to the initial state, or at least if by waiting a bit it returns to the initial state. I'll make a comment about this in a second. So electrons and spins we want to steer, and I'll try to walk you through three little experiments where we attempted this. So one thing we're all well aware of, I just want to highlight this again because I'll be talking about experiments in the solid state, is if we create an electron hole pair, if we excite the carrier in a solid with coherent light, this interaction is coherent, right? So at moment zero, in the zeptosecond where the photon is absorbed, if this can be so well defined, electron and hole are a coherent object and know of each other. So for like our ultra-fast laser ideas, the state-of-the-art photonics would be I can create an electron hole pair in a femtosecond or an attosecond or how fast you want to call it. Now, interestingly, state-of-the-art electronics, so my computer runs at gigahertz clock rates, right? And faster than this is not possible. And there are many reasons for this speed gap between what we photonics community can do and what state of the electronics can do. One of the bigger reasons, I think, the one quantum reason is of course all these couplings and interactions that conspire to take this initial coherence that would be in an electron hole in a photodoping process that immediately is sort of cascaded and dissipated away, and everything is made turned into a thermal mess. So I just want to reiterate the aspect that, again, we're all aware of, but in these transistors we're using in the computer, we can very quickly turn it on, nanoseconds or even half a nanosecond. But if you want to reuse the same resistor for information processing, you have to wait. So the turning off of the transistor is not an active step in electronics, right? We turn it on, we make it conductive, and then we wait for this conductivity to decay naturally by all these dissipation channels. But that imposes the fact that we cannot actively turn it off because it's not coherent interaction, it imposes a strict limit on how quickly you can manipulate because you have to wait for it to return into the initial state. Now, one extra comment, in atoms, we are totally used to coherent control, right? As Lou said, this lives picoseconds. Coherences in atoms and isolated systems live long. In solids, they really, really don't. And this is what prevents us to apply coherent control protocols to room temperature solids. Now, this is not so true for 1 Kelvin solids. Then you can apply some quantum computing tricks, but for room temperature, you cannot, because you would need to be faster than all these dissipative cascades. And the experiments I show you try to get as fast as they can to maybe outpace some of this dissipation and loss of coherence, which is not the same. So the optical antenna, there was a famous experiment in the 80s, the Austin switch. So they noticed, so in 80s language, they took super fast lasers and noticed if they photodope a piece of semiconductor, it suddenly becomes conductive. And this sudden onset of conductivity they could use to chop an external electric field, just measure current, turn this semiconductor conductive at different times by laser illumination, and then use this Austin switch to measure quickly varying electric fields. So linear photodoping and then a DC field effectively to drive a current in the conduction band. So then back in Garching and Ferentz's group, we took this idea a bit faster, I should say. We tried to get as fast as possible. So that would ask for a large band gap. And then we concluded that, okay, quick excitation is in the tunneling regime. So we replaced the single photon ionization by multi-photon or tunneling ionization, if you want. So that would narrow down the effective length of this ionization or photoconduction event to a fraction of the laser illumination duration. And then we checked how the current temporally evolves, that the second light field drives with these carriers that suddenly become conductive. Now, this tunnel ionization step, this really strongly modifies the electronic structure of your illuminated samples, right? So in these strong transient modifications, they are not good for coherence. So this is a scenario where the system is strongly perturbed. And then one shall not think of some 1-2 innocent excited carriers in the unperturbed band structure. This picture in the strong field regime is surely not applicable. So this works, but it sort of auto-accelerates the decoherences by applying the strong field. So we thought, okay, we need yet another step. And what we did then is we decided we would go for linear excitation. And this is where it becomes now loose talk again. So we would synthesize an attosecond or sub-femtosecond pulse that singly photon ionizes the band gap of a large gap dielectric. So what I will show you is lithium fluoride, the dielectric with the largest band gap, 14 eV, radiation, an isolated burst resonant to the lithium fluoride band gap. Okay, so single photon injection, and then this is really totally analogous to the Austin switch, except that this injection event is less than a femtosecond in duration. Less than a femtosecond in duration means that maybe then we have a chance to see some residue of coherence if we quickly grab these carriers and then push them around in the conduction. So attosecond resonant injection and an optically gate field. And let me briefly walk you through this experiment. So this is just a standard pump probe, synthesize sub-femtosecond isolated pulses between 10 and 20 electron volts. And the observable now is not transient absorption or photoelectrons or ions. The observable is a current running through two electrodes that are attached to the sample we want to study. So the sample we wanted to study, as I said, was lithium fluoride. But on the next slide, you will need to stretch your mind. I will show you comparison of this experiment, two gold electrodes attached to lithium fluoride, and the experiment where I removed the lithium fluoride and just fill the gap with neon gas to go back to the atomic case and do a comparison. Again, pump probe scheme, standard attosecond pump probe experiment. The observable is a current in an external circuit. So the experimental data I show you are truly interfaced to electronics. This is not a polarization response or some effectively optics measurement that then somehow we route back to an electronic response. We measure it through currents in an external circuitry. Okay, and this works well. So for the connoisseurs, this is a comparison between the streaking and this, we call it photoconductive sampling. And this works also for very long traces. So for streaking, this would take probably days to measure. With this photoconductive sampling, you see you really, for a short light burst, you really see all these wiggles and you learn it's actually always some noise floor in such a short light pulse, right? Okay, now let's try to think of an atom as having a band structure. So if an XUV photon ionizes an atom, you could think of the core level, or you could think of the core level as the valence band. This has no dispersion, of course, it's a localized state in the atom, right? So let's think of a neon bound electron as a flat valence band. So this is now my fake band structure for neon here, energy and momentum. And the conduction band after photoionization into the continuum is just the dispersion parabola for a free electron, right? So this would be the conduction band. Once the electron is free, you can accelerate it to any velocity you want. There are no voids in this conduction band, nothing. Just a free electron dispersion parabola. Now, in the experiment we did, and I start now with the lithium fluoride removed, just neon. This is the attosecond or sub-femtosecond pulse that injects carriers. So here in red is the whole population in the flat valence band. And in blue is the, laser pointer. And in blue is the electronic population in this conduction band, free electron dispersion again. And you see the light field pushes them back and forth, the streaking concept that we've seen many times, including the previous talk. So what I pick up then as in the external electrodes is a current that either goes the one way or is a current that goes the other way. And which way it goes is predefined by the arrival time difference between this the XUV injection pulse and the red gate pulse. And what I show you here is four such measurements for different peak amplitudes of this electric gate field. Now, these are normalized and scaled to size. What I want to show you is that even for the biggest field amplitude we could apply, the recorded electric field vector potential coincides with the scaled up version that we recorded for a very weak gate field. So all this shall tell you is that if we apply this photoconductive sampling in the gas, then this is a very good and intensity ignorant method to measure your electric field. So what you get out is actually the vector potential of the light field you put in the gas phase experiment. Now, this changes if I plug in lithium fluoride. So lithium fluoride, you see the first wiggles of the pulse. If you compare the very weak gate field setting with a very strong gate field setting, first wiggles are still okay. But then here, when the field gets strong, there are significant deviations, actually nasty deviations. So in lithium fluoride, for strong gate fields, this is not a good method anymore to measure your electric field evolution as a function of time. But we can try to understand these deviations. And the deviation, of course, is in the band structure of the material. And here's the band structure. So I should say it's computation, one-dimensional computations only, computations by Christoph Lemel and Burgdorfer group. Same system, here lithium fluoride, the XUV pulse comes, it promotes carriers into the conduction band. The gate field shakes them around, but then it becomes dangerous. If the gate field is strong and pushes the carriers to the Brillouin zone edge, some of this coherent population of this wave packet couples to the higher conduction bands. And then it gets messy, because if then the electric field, the gate field turns around, it suddenly drives a current in different conduction bands with different curvature. Some of these currents actually go the opposite way. And even worse, if this wave packet then is pushed across this avoided crossing, again, some of the population is coupled into even higher conduction bands, as long as there is still some coherence in this wave packet, I should say. Anyways, for this 1, 2, 3, 4, 5 femtoseconds, there is enough coherence to see this population transfer like a ratchet. Whenever it's moved, the wave packet, some of it couples into the higher bands and then ends up messing up several bands. So here would be the concept again, the injection, then the gate field takes it, pushes it to the zone boundary, coupling into the higher band, and then even diabatic transfer across avoided crossings. Now, there's no time to go into all the details. I just want to advertise that by reconstructing this, we really get access to an interesting quantity. We get access to the time-resolved population of individual conduction bands. So we can really tell at which moment in time, which conduction band is populated to what degree. So I think for more complex electronic structures, this will help us in the future to understand how they actually interact with complex excitation fields a bit better than our current knowledge. Anyways, what I want to highlight is, as long as these currents are a bit coherent, so they are, of course, this coherence very quickly disappears, but in femtosecond 1, 2, 3, some of it is still there. These currents can get quite exotic, and I want to briefly show you one example. So now think of nickel. And I will show you a few electric fields we were sending through nickel, and then we time resolved the laser pulse after it has interacted with nickel. Of course, nickel is intrinsically conductive, so it doesn't need to be excited first. The strong field immediately drives some currents, but if it's really strong, it also excites into higher bands, makes very complex population situations, and then drives this resulting very complex currents. And I will walk you through a few extreme but quite interesting cases. So here is the incident electric field as a function of time, and here's the transmitted field. Well, it's weaker. That's good, right? Some is reflected, some absorption. The transmitted field should be weaker. Now, if I take the same pulse and shine it through nickel at higher intensity, but same pulse energy, this is important. Higher intensity, same pulse energy, so same number of photons if you want it. I suddenly find that more light is transmitted, more electric field is transmitted, though I don't put more field at the input. That in the first second disturbed us a bit, and I think you know the process. It's called saturable absorption, right? If the intensity is high enough, the sample gets a bit more transparent than it intrinsically is. So then we thought, okay, more intensity, let's see. So this is the same, this is nonlinear optics if you want. Now, same experiment, more intensity, as much as the nickel can stand. Super nonlinear optics if you want. So at an even higher intensity, so intensity that totally saturates the saturable absorption, even more field goes through, though we don't put more energy in the input. And then we go still a bit higher, then something disturbing happens. Suddenly, the field gets weaker again, the transmitted field, but it pulls forward in time. So it literally pulls forward. So the group moves faster than it does at low intensity setting. So it accelerates. Not only the phase, the group accelerates. Disturbing. I show you one more example. So this was the strongest intensity setting we could apply. This is a 4 nanometer nickel film. So intrinsic transmission is about 70%. And we actively cooled it. So it's attached to a diamond that is cooled to have the opportunity to apply the strongest field it can possibly stand. So this is the incident field. And then at the most insane intensity setting, that's the transmitted field. And what you see is, okay, transmitted field is a bit weaker, but the transmitted field arrives about 700 attoseconds earlier than it would arrive if there was no nickel. So we checked and checked and double checked because we were afraid of superluminal propagation. It is really superluminal propagation, but I learned that this is not forbidden that the group velocity goes faster than c. This is not to be equated with a signal transmission velocity, which always stays smaller than the velocity of light in vacuum. But here, the group velocity accelerates significantly. So 4 nanometer film, about a quarter of the wave phase shift. So this is a strong phase shifter. So about 25 times the layer thickness worth of optical depth is induced by this nonlinear current driven in the sample. And if you compute this, is a bit brute force to translate it into a change in real part of refractive index, but this goes negative. It gets transiently negative refractive index of like index minus 20. So alarming numbers. But these super nonlinearities are something interesting. We want to dig in deeper. And they exist as long as there is some coherence in the excitation. Let me invest a few minutes to comment on another thing. So if we can control charges very rapidly, is there an opportunity that we could also control spins very rapidly? And that's not trivial, right? Because of course, to each charge, there's a spin attached, but spins also interact in multiple ways. So this would be for the magnetists, the typical time map. We can coherently modify the electronics, but then the spins do what they want. I think the proliferated joke in magnetism is that they claim they want to predominantly take nickel electrons and pump it into platinum final states only for the one spin direction. So you optically pump away spin population from the nickel. So consequently, nickel is expected to demagnetize as quickly as we can drive carriers across the interface by the electronic interaction, which is faster than spin manipulation. Okay, this works. I skipped the animation because in the video you in any case won't see it. In this interface system that I'm showing you, we could show that within 5-10 femtoseconds we can really demagnetize this nickel-platinum interface completely. That was the fastest control of magnetic state seen until that time. But it's only unidirectional, right? We can only make it less magnetic. And now we were thinking, can we make something more magnetic? Now, unfortunately, I can only show you a teaser, not the final answer. But I want to conclude with briefly mentioning a second experiment along this line. So for the experts amongst you that know what the magnetic tunnel junction is, you will recognize the magnetic tunnel junction is a resistor, and its resistivity, so an oxide layer sandwiched between two ferromagnets, and the resistivity depends whether the two ferromagnets are parallel magnetized or anti-parallel. So in anti-parallel, there's no conductivity. In parallel, there's a lot of conductivity. And we thought, okay, we want to understand this system a bit better with our time-resolved techniques. So we took a tunnel junction, removed the top ferromagnet layer. So this you see here, and apply time-resolved time and spin-resolved photoelectron spectroscopy to see how the magnetic domains in the interface between the oxide and the ferromagnet looks. So this is only half a tunnel junction, to be fair. But without, with sparing you the details, what you can see here, so this is the grayscale images show the contrast, the magnetic domain pattern. It's a spatially resolved measurement, the photoelectron microscope. You see as a function, so this is the intrinsic state, then we optically pump it, and you see by eye that the contrast, the magnetic contrast is enhanced. So this looks as if it gets more magnetic by shining light. Is that possible even? Because shining light in the end means you put more heat into the system. It shouldn't get more ordered as a response to shining the light, right? But I think we found a niche there where it actually magnetizes. So the photoelectron spectroscopy is also energy resolved. So I will show you the temporal evolution of the magnetic moment for 3 segments of the density of states around the Fermi energy. So yellow is photoelectrons around Fermi energy, green is a bit deeper binding, and blue is yet a bit deeper binding below Fermi energy. The one pulse kicks them out, and we measure contrast, and then we see how this contrast changes as a function of time, arrival time difference between the light pulse that creates the dichroism image and the light pulse that electronically excites the system. Again, spin selective in the same manner as it did in this nickel platinum sandwich. And here is the result. So the colorful lines are the temporal evolution of the contrast. So now this is not attosecond or femtoseconds. This is actually long-lived changes of the magnetic state. So you see for the most weakly bound electrons, we do laser-induced demagnetization. But then for those from lower energy regions, which are actually more, the contrast dramatically increases. So in this system, in this parameter niche, we indeed induce magnetic moment by absorbing light. And the coolest thing, I have to admit, we do not fully understand it yet, but the coolest thing about it is that these grayish lines also show you the population in this energy interval, the change of population induced by the light burst. So you see that these changes to the magnetic moment outlive the change in electronic population. So that means the light pulse comes, it reshuffles electronic occupation. This reshuffling of electronic occupation changes the spin system, and then the electrons thermalize, cascade down to their initial states, but the system is left in a more magnetic state afterwards. Okay, now we have to understand this and then work a bit more along these lines and see whether we can actually find more parameter niches where we can use this exceptional degree of control we can exert over electronic properties to also, in a very controlled and bidirectional fashion, control magnetic properties. Okay, and with this, I want to conclude before Giuseppe gets nervous. So I hope I showed you 2-3 marginally convincing examples that with these ultra-fast laser fields, we can manipulate electronic states. We can also manipulate spin states. And what's the beauty in this? The beauty, I think, really is if we do this electronic manipulation super, super fast, maybe there is a time window before all these dephasing thermalization channels set in. Maybe there is a time window where we can think of this applying coherent control protocols that we know from atoms and isolated systems also to real world solids. Now the price will be, we will have to be super fast in manipulating, right? Thanks for your attention.
So thank you, Martin. And of course, we have time for questions.
Giuseppe, can I ask a question?
Sure, Lou. Please go ahead.
Martin, very, very nice work. Listening to you talk about, this effect, that strong field, was kind of reminding me of, slow light that people discussed. Is there, do you have an interpretation? Is this some type of time domain analog, this slow light?
Yes, I think it's actually a very close analog. So now I'm not expert on this, that I should say before I say what I have to say. But it turns out slow light is effectively, at least the way I know it, is you use a system where you know the energy levels, so one of these lambda systems, for example. Then you saturate one transition, and then in the other transition, by this artificially crafted population on the one channel, you can make the refractive index or the dielectric constant along the other transition. You can manipulate it, right? It's across a resonance. You would already in a simple Lorentz-Drude model, you would expect the refractive index to go maybe below 1, maybe even negative, depends a bit, right? But below 1 across, right above the resonance, you can. Now, you cannot use this in real life because the resonance is narrow band. So for short pulses, it doesn't work. And the refractive index is below unity. At the same time, the absorption is crazy high because you're just at resonance, right? So now, if you want to have this refractive index below 1 or even below 0, you somehow need to artificially create a situation where you don't have this simultaneously too strong absorption. Now, blah, 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 blah. The slow light applications where you pump your systems and then you see at another wavelength that propagation is effectively an entire cycle, is a continuous cycle between absorption, re-emission, absorption, re-emission, absorption, re-emission, and that makes the propagation slow. You can sort of time invert the entire idea. You could, if you really hinder absorption, you push out the light field that you coupled into the system on the other side too early because you really don't want to absorb it if you saturate the absorption by something else. So that is a bit my hand-waving take on this.
Yeah, very interesting.
But I think this is the picture that I think sounds most reasonable to me. Like you couple light into the system, then you suddenly completely, because it's so intense, it's a self-inflicted effect, right? It completely changes the population distribution. And then in this new electronic structure, the new dielectric coefficient, this light is not supposed to be inside. So it pops out too early, I would say, yeah.
Yeah. I mean, one of the keys in the slow light was this idea of storing the coherence in the system, right? In the atomic system. And that's why later on you can read it out.
Yes. But you could also think of this pushing the coherence forcefully out of the system, right? And then the energy has to leave. Yeah.
Thanks.
Martin, I will have a couple of questions. The first one, it's in the last data that you showed, there are some oscillations. Are these phonons or?
Here?
Yeah, I mean.
Yes.
Also,
Yes.
Yeah.
Giuseppe. No, it's not phonons. The frequency is completely off. We believe it's magnons. It's actually spin wave excitation, but there's an issue here. The spin wave, there's dispersion relations for spin waves. And this is the frequencies we see is about a factor of 2 too slow. And now we are talking to theory to see whether, if you think of bandgap renormalization, if you take an electronic system and heavily pump it, you expect bandgap renormalization, right? Now, is the same true for a magnon dispersion relation? If you populate the magnon branch heavily, do you obtain frequency shifts? I don't know yet. It's my current suspicion, but I don't know yet.
So let's say you expect to observe this oscillation, but the frequency it's a factor 2 off. But you would expect to see.
The thing is, do you expect it? Magnetism is a bit dangerous, right? Because everything has been measured with MOC already. So the magneto-optical Kerr effect. But these measurements are extremely difficult to interpret because they are not energy resolved. And it's somehow a mixture between changes in the electronic response and then also changes in the reflectance that is eventually detected due to electronic rearrangements, right? So some of these more subtle features can be hidden in MOC measurements. Now with the photoelectrons at the price of all the nasty photoelectron complexity, you see some of these things a bit better. But then, the short answer is I believe it's spin waves, but we still have to prove. Yeah.
To prove, okay. Thanks. No, it's interesting.
Because it's still one more sentence. It's a heavily pumped system still, right? And we see this oscillation period to change if we pump harder or softer.
Okay.
Yeah.
Thanks. So other questions? Maybe I can then pose my second one, Martin. So in the lithium fluoride now, you you at high fluencies have high intensity these changes in the electric field, in the measured electric field.
Yes.
Can I interpret, the measurements in this way that when the electric field is so strong that I cannot use anymore this parabolic approximation for the dispersion, then I will start seeing differences, or I really need to reach the edge of the Brillouin zone?
Yeah, this is, I would even say it's the same. So if you create a wave packet that is very narrow and located at the conduction band minimum, let's say 100 millielectron volt wide, you can push this very far, right? So the spectral width of this first conduction band in lithium fluoride is about 4 electron volts or so. Now, of course, if you want fast response, you necessarily need to launch a wave packet that has a certain energy spread, right? Let's say 2 electron volts. But then the price of this is fast, but then you can't push it so far because its outskirts will reach Brillouin zone edge and then couple to the higher bands. So your first part of your statement that, as long as the wave packet you create and you want to steer around stays in the parabolic, in the minimum that is well approximated parabolically, is fine. But then you probably didn't max out the bandwidth that your system has. So you you chose to make it a bit slower.
Okay.
Yeah. But this is nasty, right? Because in the next band, it has opposite curvature. So not only it doesn't contribute to the current you want to detect, it actually makes a current that eats away from the current you want to detect because it goes the opposite direction.
Okay, thanks. Interesting. Yeah. So
I think I can stop the screen sharing, probably, right?
I'm looking around, but I cannot see any other question. So I would say, let's thank Martin again, also Lou, for this beautiful presentation, and we can close this afternoon session here. So have a nice evening and see you tomorrow then. Bye-bye.
Giuseppe, bye, Barry.
Bye-bye.
Bye-bye.
Bye-bye, everyone. Bye, Reinhard. Bye-bye.
Sehr schön, Martin.